Like, they'll get mad at me, and then by the time I come
Alright, let's hopefully the note sheet, yeah.
I need to see this. I need to see this.
Let's come together now, and thank you. I appreciate your help, one with the other, helping one another out to do this if you forget, or if you have never done it perhaps even. But hopefully those things we just did in the warm-up could be treated as prerequisites today. You know how to enter data in your calculator and run a linear regression. Get that regression be stored in y equals, use zoom, stat, get the r and r squared values and all that kind of stuff. All of that, now, not all of that is something you understand maybe, but we'll say a little more and refresh your memory about these things. Okay? As usual, some of this will be some review for some people, so just let's be patient for those who know nothing about any of this. I think that we all have varied experiences. Some of us have a strong background in some of this from AF. Some of you have an even stronger background because you've been in AP Stat this year. Some of you have a varied set of experiences from your Algebra 2 course if you were a freshman somewhere else too. So let's be patient with one another and help each other out along the way. So there are a number of things I'd like to address today, 3 in particular, that are comma separated at the top of this document. Correlation, talk about that a little bit, and regression we'll do first actually, and this idea of re-expression as well. So just in case, just because we always like to do this, in case you want to know what's happening under the hood when your calculator is doing this linear regression, this is the calculation it's doing. Now, we won't go into great detail about why this produces like an optimal line, because really it takes some calculus. Anytime you have an optimization problem, you're dealing with like finding mins and maxes of a function. So we'll just provide these results without justification, unfortunately. But someday maybe you'll take a calculus-based statistics course. You can work this out actually. I can hand you a book and point you to the right chapter if you want to see the whole proof of this. So the regression line you got from your calculator, I'm using this notation here, this y hat with this little caret above the y, to mean the regression we produces y values that are not the actual y values that go with the x values you plug into. They're estimated y values based on this equation, which is kind of operating as an estimator of y values. The slope is given here with symbols that mostly you understand. The subscript might be a little confusing. What do you think mu sub x means? Yeah, that's the mean. We have to subscript it because now we have like 2 means in our lives. We have the mean of x and the mean of y. And sigma x, similarly, is the standard deviation of the x value column. And if you square it, I guess that's the variance of the x column. The y-intercept is given this way, and this allows you now, and we've seen these things, you could actually calculate the linear regression without the actual linear regression feature on your calculator. If you calculate each of these constituent parts and then stitch them together, you would get the equation of the line of interest here, the line of the regression line. Notice for the y-intercept that it uses the slope. So this is actually a little bit of a messy calculation. If you haven't already calculated this, then you really have like a big formula here. So maybe you do this first and then you calculate this. The only symbol I didn't explain just now is the mu sub xy. And that can be explained as this quantity right here. It's what would happen if you want to calculate by hand. It would be what would happen if you would multiply every x and y value on your list and create a third list of the products of each pair of every point, and average those. So that's the mean of the product xy. Why does that give some measure of variability between the data sets or some relationship between them? We'll leave to another course. But you can just know right now that this entire numerator, the quantity up there, is called something called the covariance, and it is a measure of like how much variance the 2 random variables have with each other. Yeah.
Will we need to like do this? Like be able to do this?
No. Like I said, I'm just like the other things, though, I like you to know what's happening under the hood, though. Just like standard deviation, or just like normal CDF. I think, in fact, you're the one that asked us the other day. Is it okay don't ever, if we just use normal CDF, I'm like, well, yeah, I just also want you to understand, or no, we were talking about these scores, like you, right, you were like questioning that, and I was like, well, please, I just want you to understand what's going on. So I just wanted you to see where the calculator is generating that equation from. But no, I don't know that will make you go through that process really. So you could try it with the warm-up problem just for one time and see that it does work. See that I'm not lying to you. Okay. Good. I guess we should also pause and just say this. This is the first time, I should have said this at the beginning, but this is the first time we've encountered bivariate data. You might be thinking, haven't we already plotted like a bunch of stuff in this unit? The answer is like, yeah, but not like two variables, two random variables. We've dealt with one random variable, and on the y-axis sometimes we'll plot the frequency, but that's still only one random variable. We're like thinking about only one measure in a population. The number of TVs people have, or the length of weeds around this McDonald's house, or whatever it might be. But it's only one thing. That's it. Whereas here, you notice we have two different, completely different random variables that we're somehow making statements about together. All right. The next item on our to-do list today is to say something about this one number figure that gives a measure of how strongly correlated two random variables might be. And it has a long name up here. It's called Pearson's product moment correlation coefficient. And that's called R. And like it says on your paper, this can quantify how good your regression was, right? You got a linear regression, but it gives you also a measure of how good it is, right? And I know some of you know this because I've read it in your IAs as I've been looking at them. You've done some work with this number to help justify why a regression might be good. It's not the be-all and end-all, but certainly it's true that if you get a number close to 1 or -1, then you have a fairly strong correlation, perhaps. What was the warm-up one? What did that come out to be? It was negative something, wasn't it? Okay, it's negative 0.94, tells me that it's not bad, it's pretty good, and that it's a negative correlation, right? And you saw that on the graph, too, that there was a negative correlation. Did you graph it? Yeah.
Why is there a difference between like -1 or 1? Like what does that mean if it's closer to -1?
Yeah, so what does that, I guess I just said it, what does that mean? Yeah. It's going downhill.
Oh.
Yeah, so an increase in X produces a decrease in Y. And we should always say this, yes, I know some of you have already said this today as we've been thinking about this. But yeah, we want to say, we do want to say that any correlation that this might be speaking of, even if it's the strongest ever, doesn't necessarily imply that there's any causality one way or the other with the variables. We were having a discussion about this over here a minute ago. So kind of the classic example that I think is kind of the go-to example, we might have even said this when this came up in a side conversation the other day in this class. Something like this. But you can see that here that we have sunglasses sold and ice cream sales. There's actually a pretty convincing positive linear correlation between those. And yet there's no causality there, obviously. There's maybe a third underlying cause, and that's what?
Summer.
Yeah, the weather, the summer, the sunny temperature, all that. Again, this calculated value could come just from your calculator if you like, but this is in fact what this is. Again, the numerator looks familiar. It's from the last slide too. The numerator we had there too. It's called the covariance. And this is the two variances of x and y, or the two standard deviations of x and y. This is the sentence I think that they make you even, I don't know, they make you memorize it in AP Stat. R squared, the explanation of what R squared gives. This is just the previous value squared. And well, I'll read this in a second, but yeah, go ahead. No, but did I explain enough in terms of what it is in order to give you a sense of how you would do it yourself? Yeah, you multiply x and y in each entry. I probably won't make you do it that way. Yeah, you multiply them into a third column and then average that column. Yeah. We have never done this, and I don't know that we'll need to, but if you wanted to run 2-var stats on your calculator, we always keep hitting 1-var stats, right? If you ever do 2-var stats, and you have it in your calculator right now, you're welcome to do this. If you run 2-var stats on L1 and L2 right now, you'll get, in fact, a list of all the things I've been using in these equations. You'll get mu xy, for example. you'll get, and you can scroll down. They should give you like mu x, mu y, mu xy, sigma x, sigma y. They'll give you like a whole host of things, which I think will be, huh? That's the sum of all the products of x and y. So if they didn't give you mu xy, do they? In that what 2-bar stats? Well, then you can take the sum of xy and just divide by however many data points there were. That'll give you it. Anyway, give these things a try if you like. So r squared obviously gives you a positive number, and it's a number. It's a single number summary that explains. I should make you do it. All right, your test is on Thursday, AP stat people. So where's my AP stat people? All right, go ahead, Sebastian. Without looking down your paper.
I don't remember.
I won't tell. Who's your teacher? Mr. or Mrs. Okay. I will tell her how disappointed she should be in you. You have it, Maki? Can you say it? What does r squared mean? Do you have it? Someone? We can read it off the paper. Huh?
I remember now.
You do?
Yeah. So r squared percent of variation in y is accountable to the linear relationship between x and y.
Good. That's good. That's good enough. Yeah. Yeah, it's exactly the proportion of the total variation in y that can be explained by this linear correlation. So these things are set on your paper too. Like the last number, the better r squared is. I mean, the closer to 1, the better we have here. We should say something about residual plots too. For those, I think some of this is stuff like, for example, those who took AAF, you did have a conversation about, and this is one of those things. Right? Didn't you do some residual? I've never taught AAF, but like I have like my ear to the wall over there a little bit. And I'm like, I know you've done some of you have done residual plots before. So let me show you with the data we did from the warm-up today how to get a residual plot. First by hand, and I'll show you what to do on the calculator. And actually, let's actually do this. This matches what your calculator will calculate for the residuals too. What I want you to do is go to L3 and actually go up to L3 and press enter so that it has L3 down here equals and then blink, 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 right? If you're in the first entry spot, that's not good. You want to be up on the definition of L3. So I should say L3 equals blink, 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 and then type in L2 minus L1 of Y1. Now what did I just ask you to do there? Well, I've asked you to take the actual value in L2 and subtract the predicted value from the regression equation. You see what I'm doing? I'm asking you to, oh, I'm sorry. I wrote that wrong. L2 minus Y1 of L1. There we go. Y bars function Y1. So again, let's help each other out with this. So you're typing in L2, so that's the predicted, the actual value, minus Y1 of L1. That's the predicted value from your equation. Now this only works if you have the regression equation in Y1, which I trust you all still do. Right? So what it's doing is it's taking each L1 value and plugging it into your regression equation to get an estimate. And then using the real value and calculating the difference, or what we're going to call the residual, right? Once you press enter, it should populate the whole column here with the differences between the actual and the expected value from the estimated value from your regression line. This is also available as a built-in feature calculator, which I'll highlight in a minute. And then if you're plotting the residuals, you can go to scatter plot, and instead of L1, L2, like you had a second ago when you were doing the warm-up, how about L1, L3? That'll plot the residuals. And then you may want to hit zoom stat again to see the picture of all the residuals. And this is a graph, literally, of all the differences between your data and your estimated value for the data at those points. Okay,
Isn't it easier to just in the stat plot instead put for the...
Yeah, have you discovered where your calculator has the automatic feature?
Second list result.
Yeah. So there is, now that, again, I sense a trend in this class here. You like the shortcuts here, right? But again, I want you to know how the calculator calculates the residuals. So now that we've done that, you are welcome to just in the y-list as you go to plot these, you can just plot L1 and then resid. And the place where you get that list, if you've already done the linear regression, it actually makes this list for you, even though you never asked it to, and stores it somewhere in the calculator. And the place you find it is under second list. And under the lists that are available, one of them is named resid. And just select it. So go to second list and select resid. And that already has that column. It's the same as what you just computed in Y3, so there's no difference. Anyway, when you do this, you'll get a plot something like this, right? And the thing we're looking for, two things, for those who haven't thought about residuals before. We're looking for, obviously, small errors. So that's good. That would be something we're looking for. But also we want no systematic deviation from our estimate. That is, we're looking for some random scattering. If there's some kind of systematic pattern, then that indicates that perhaps it might be it's a decent fit perhaps, but it's probably not linear, if that's what you've done here. Okay, so questions about what we mean by a residual or how to interpret a residual plot. Sorry for the shotgun approach to all this. Let's now consider the depth of water in an urn. Okay, so this is a data set that's on your paper. So again, I invite you to now enter this into your calculator, L1 and L2. And we'll use this data set for the next few minutes. Let me see now, again, if my calculator is awake now. No, my calculator is still dead. I don't know how to help it. Okay, I would love to be able to show some of this up here, and I'm sorry about that. So do help each other out here. Let's do L1 and L2 as X and Y, the first row, and then the second row. Yeah. Where's Grace? Grace, do you want to do the next one?
Great.
Do you want to do another one? Oh, you gotta go. See ya. She's doing makeup work for me out there. That's great.
You are doing way
Any help I can be on the calculator?
Yeah. But she says that she doesn't understand quadratic regression. Also, I think this is like whenever the X and Y are on like with the standard things, it just puts in like the value for X. Just I think that might be because this is a saved document, and I don't know how to save that variable. Thanks, Mr. Chase.
Sorry. Everything okay? All right. So I mean, you're doing it just again what you did on the warm-up for practice. This is good. This is good. When you get a plot of this data, it looks like this. Yes. I just used the scatter plot here of the original data. When you do a linear regression on this data, here are the results I'm getting. Really good, actually. Very good R squared value. the line even looks good. I've also asked you though to do the residual plot, and I think you'll see there that the residuals are small but systematic. Did you get this for the residual plot? Something like this? Make sure you can generate this picture too. Okay? You can see that there's like a kind of a systematic error in our data, in our estimates. So now I'd like to do an experiment with this data. Yeah, we're just saying this doesn't really look linear. In fact, it looks like kind of like it has a curve to it. So this is going, again, this is kind of experimental. This is in some ways, where does it say this? Knowing how to re-express your data is part visual, right? So that's what we're doing here. We're like, well, it looks like it has a curve to it. Right? So that doesn't sometimes feel mathematical, but that's where the direction we're going here. So let's try the following. In Y3, if you will, I invite you to take the square root of your data. So do the same thing as we were doing before, like L1 and L2 have your data in it, and then L3 use as the definition of L3 the square root of L2. Yes, so actually define, so you got L1, L2, and you've got your data, and then actually when you go to do L3, like we were doing before, click on it, and then down where it says L3 equals blink, 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 actually type in the square root of L2. Okay, and it should, once you press enter, populate the whole column with square root of all the values in L2. And then, when you're ready, run a regression of L1 and L3. Okay? Tell me how that goes for you. In fact, I mean, you can see it on your paper as well. The regression you get should be the same thing I have too. But of course, once you get that regression, realize that it's not a regression of y on x. It's a regression of the square root of y. The square root of y with x, right? I'm leaving people in the dust. Oh, maybe this will work. Can I put my calculator under the light? Can you see this if I type stuff in here? Hey, that's not bad. Okay. This is old school, but we'll do this. How am I doing here?
Online calculator magic.
I'm just going to check my data here. All right, looks good. All right, so I'm going to go, I assume you already did the other things, but let's go to L3 and define that to be the square root of L2. And now I'm going to do a regression, linreg, L1, L3, and I'll store this in Y1 just for fun, okay? Oops, I don't have my diagnostics on. What's that? I'm doing it. Is that what you got? Isn't that what I have on the paper too?
But that's what I got too.
You'll find that the other time you do that and by annoyed are positively correlated to an extreme degree.
I guess maybe this is just strong. Okay. Alright, yeah, it should be negative 0.005 x plus 3.5295. Okay, so that's, yeah, I'm going to blame my previous class for not catching that here. So, okay. You guys are more savvy than they are, apparently. Okay. Anyway, good. So let's update that regression. But no, keep in mind, even though the calculator says it's y equals ax plus b, it's actually the square root of y equals that. All right. So then, how do we recover y? Is still the question at play here. And yeah, and I think squaring both sides of that equation will do the job nicely, right? So let's change those two numbers. I apologize. To the ones I just wrote down here. More things. Negative 0.005 approximately. And 3.53 approximately. Okay. So squaring both sides of that gives you the quadratic that we're looking for. Y equals. Now, what's interesting about this quadratic? Anything interesting about this quadratic? By the way, did the r squared value look good for that? Much better. Yeah, in fact, like, really good. Really, really good. If you look at the plot, too, if you look at the scatter plot and the linear regression we just did with L1 and L3, I think you'll find that it looks really good, too. So I think we feel really good about ourselves. I even used the word wonderful. Yes, I think we can all agree. Let me ask you this, though. I mean, this is interesting. This is an interesting trick I pulled here. The kind of quadratic I produced is special. Do you see anything special about it? I don't know. Is there any unique feature you'd like to highlight in particular? Maybe, do you notice where the vertex is? It's quadratic. It has a vertex somewhere. I don't know where.
Somewhere on the graph.
I can't deny it. Go ahead and find the vertex. Yeah. Algebra 2. List operations. All right, where's the vertex? You're all fired.
Yes, I can go home.
No. Wait, come on, you're out for 2 seconds. I don't really want to talk about it. Find a vertex.
I would, but I'm too lazy.
You know how to find the vertex?
No. It's very obvious. No one knows how to find it.
What are you doing? People who have a strategy right now. What are you trying to do?
I'm
Drawing
waiting
it?
for somebody else to do it.
Waiting for someone. Yeah, that's
My calculator's not strong.
find the minimum. Okay. Huh?
My way's better.
Yeah, an interesting insight from this side of the room. Maybe that's vertex form. Well, actually, not quite. It's whatever makes this 0, though, right? Yeah. So that's not 3.5. Well, you need to put. Yeah, we need to put something in for x that gives 0. I mean, it's basically vertex form. Can you find the roots of this quadratic? The 2 roots?
Wait, is it negative 706?
Yeah.
And then it has
I think it should be a positive number. I don't know. Just looking at the equation. What did you say? 700 something?
706.
Comma what?
Comma 3.29 times 10 to
Comma 0, right? I mean, isn't that right? I mean, the two roots of this polynomial are, well, it should be clear from the form of this expression that the two roots of this are the same, aren't they? Right? It's
Not
just-
quite.
no, yes, quite. They're exactly the same. It's got two equal factors, doesn't it?
Oh, yeah.
I just, right? There's only one root, and that means it's sitting on the x-axis. I don't really care that it's 700 something, but the point is it sits on the x-axis. And so this is a big assumption for what we did here. This idea of squaring it, and then taking the square root and then squaring it, really only works with quadratics of this form where they have a vertex on the x-axis. Now, in the end, it worked pretty well, though, because we got good results. Or did it? Now I want you to think about the fact that maybe our squared values are not the whole world. Tell me now what this indicates for the water in the urn. That's what this is supposed to be, right? What does that indicate about the future behavior of the water in the urn? Huh? What's it going to look like? It's going to go back up. So I want you to be careful because maybe, even though it was a really good fit, maybe that's not the be-all and end-all, right? Maybe we need to think about what this model really says. And I think maybe, anyway, so, huh? Yeah, you could limit the model, but still, you need like maybe a good reason to believe that it's quadratic. All right, we did not, as you can see from the note sheet, we did not quite get through this. So do to the extent you were able this homework, okay? Which I think makes you doing. I think you can do everything but. I don't know. Maybe some of you already know how to do it. Yeah.
You know, there's this wonderful thing called the internet.
Or you can read the rest of the note sheet. Yeah. So we'll give 3 and 4 a try if we like. But do the best you can. Bye everybody. See you tomorrow. Thanks for your participation today.